Hi everyone, my name is Ile. I'm from the University of Auckland. Today I will present our work VersaTouch, the system that we developed to support touch interactions on everyday passive surfaces. Touch interaction initially started from electronic devices. Today research has shown that everyday passive surfaces could also be leveraged to support touch interactions. Compared to handheld devices, these everyday surfaces even have some advantages, such as they have very large area. Research has also explored technologies to sense touch on everyday surfaces for a long time. Here I list some of the research that are most related to ours, which are acoustic-based techniques. However, I cannot go through one by one because time is limited. Please go and look at our paper. This is a short video shows how the system works. It can sense both the touch location and the force. As you can see, there are two parts here. First part is actuator that attached to the fingernail. It sends acoustic signals, and the signal then propagates through the finger and the surface, and finally captured by three sensors. By analyzing the arrival time of the signal, we are able to localize the touch location. The touch force could be extracted by analyzing the signal amplitude. This is a calibration for the system. To calibrate the system, users need to touch 3 points. The 3 locations should be collinear with 3 edges of the triangle. Then the system will collect data and calculate the length of the edge. Finally, the system will just build up a coordinate and localize the touch. The calibration might have error. However, as you can see on the figure, when the finger is 10 millimeters away from the line, the calibration error is only 0.16 millimeter, which is even less than the sensing error. So we think it could be ignored. Calibration is not needed for every scenario. It's just needed for the touch localization, and we will show some demos later. The basic functionality of our system is to localize touch and sense force. However, it also has other features. For example, the system itself can support multi-touch interactions by multiplexing multiple actuators. And secondly, the actuator could also be used as a channel to provide vibrotactile feedback. Although it's not evaluated in our paper, we do develop this functionality in our prototype. This is the implementation of our system. We use a MacBook to control an Arduino Duo. Then Arduino Duo will send a signal to control the TNC, which controls the actuator. Then the signal would propagate through the finger and the surfaces and captured by the piezo. The Arduino Duo then get the signal from the piezo and send the data to the MacBook. Here is a detail of our customized microphones. It consists of a piezo which has a diameter of 20 mm and a 3D printed weight. The weight is to make sure the sensor contacts the surface well. And we also conduct several studies to evaluate the sensing capability. The first one is evaluating the layouts on an area of 400 mm by 400 mm square. We tested 4 different layouts. Here's accuracy for these 25 dots. As you can see, the largest error happens to the corner, and for all the layouts, the average error is around the 10 millimeters. Now we don't see significant difference between different layouts. And we also tested our sensing accuracy on different surfaces. Here we tested 3, and similarly, also the large errors happen to the corner. Then we also tested our force sensing accuracy. As you can see, we test since all the sensors are the same, we only test one sensor, and we test 3 different distances. And we also test the same thing on 3 surfaces as we did in the previous study. Here is the data plotting, and we found that log model has the best performance. And here, and we use log R because this is the performance of the FSR we use to capture the ground truth. So The log value of the resistance has an average error from 0.06 to 0.08, and this is to make it clear what does the error mean. The error actually means when we try to calculate the pseudo force of the FSR, the error range is almost like this. And our system provides 4 different interaction design spaces. The first one is sensing layouts. Users can change the layout to design different interaction. And the other one is, second one is input modality, which is touch sensing, localization, and force sensing. And we can also change the number of actuators, and the system itself also provides variable tactile feedback, and this is customizable. Finally, we introduced 3 different applications that we built. First one is a keyboard, a quickly drop keyboard. Users can just play after calibrate all the keys. The second one is a game. Users can just touch the printout paper to play the game. And the interesting thing is, because we used our system can distinguish the touch source, can distinguish users, so it can count scores for different users. And finally, this is a brightness controller. Users can just slide to control the brightness, and it can also move the sensor to change the resolution of the controller. We did not put all content in the presentation due to limited time. Please look at our paper, and if you have questions, please post it online and we will try our best to answer it. Thanks for watching.